This is our second lesson on enzyme kinetics and inhibition, and we'll be looking at the Michaelis-Menten equation. This is reflective of a model that was developed by Leonor Michaelis and Maud Menten in 1913, and as we'll see, they made some simplifying assumptions in the development of this model. So let's follow their logic. Let's return to that simple reaction scheme we saw in our last video, where we have enzyme binds a single substrate, we form the enzyme-substrate complex, that is rapidly converted to product, and we regenerate the original form of our enzyme. So this is our first assumption, as noted in the lower left of your screen here. We only have one substrate and one product, and it truly is a simplifying assumption. Most of the reactions within the cell involve two substrates or two products or perhaps both. Still, this simplification will allow us to develop this model, and we'll see how we can apply the model in appropriate ways, and we'll also see some limitations. So remember those rate constants? Here we have K1, that's our rate constant associated with forming the enzyme substrate complex. We could also have the substrate dissociate from that complex without ever forming product, and so that's our rate constant K minus 1. So you'll notice here we have double arrows, meaning we can form or dissolve that enzyme substrate complex. Also, we could start with that enzyme substrate complex. It could be rapidly converted to product, and that's our K2 rate constant. Notice in this case we have a one-way arrow. That's our second assumption, as noted in the lower left of your screen. We're going to assume that K2 is irreversible. In other words, the rate at which substrate is converted to product is so rapid it never goes in the reverse direction. Note we only have a one-way arrow here. So that's our second assumption, and what that allows us to do is eliminate one of our rate constants, and that's going to simplify the algebra for us, and that's always a good thing. So the K2 rate constant, that represents the rate limiting step. So now we have an expression for our velocity. Remember, that's the rate at which we increase the concentration of product over time, and looking at our simple reaction scheme here, that's simply going to be equal to K2 times the concentration of ES. So now we have a simple expression for our velocity, but remember, theory is fine, but if we have no way of measuring it in the lab, we cannot prove the theory. And here's our first problem. We can't really determine the concentration of the enzyme substrate complex. In other words, we can determine how much total enzyme we have, but how much is bound to substrate. That we can't really measure. So our goal now is to find a way to replace that term, the concentration of ES, with something we can actually measure in the lab. So again, here's our simple reaction scheme at the top. We recognize that the rate of change of the concentration of ES over time is going to be equal to the rate at which it forms minus the rate at which it is depleted. So the rate at which it forms is simply K1 times the concentration of E times the concentration of S. So you'll notice here K1 is a second order rate constant because it depends on the concentrations of two things. That's the rate at which it forms. Once we form the enzyme substrate complex, we can go either left or right. We can decrease the concentration of ES simply because we dissociate substrate or because we make product, and so we need to include that in our expression as well. So here we have first the expression that involves the dissociation of substrate from the enzyme substrate complex. That's K minus 1 times the concentration of ES. And then here's the rate at which we form product, K2 times the concentration of ES. So here's our expression. We're still moving towards replacing that term, the concentration of ES. Let's look next at how these things change over time. So remember, at any given time you have the free enzyme, you have the substrate, you have the enzyme substrate complex, and you have the product. Let's see how the concentrations of these change over time. First, as we saw in our last lesson, substrate concentration is going to decrease over time and product concentration is going to increase. And that's going to occur in a fairly constant rate over time, and the decrease of one matches the increase of the other. And again, that's because we have one substrate and one product. Now let's look at what happens with the free enzyme, the concentration of E, and the concentration of the enzyme substrate complex. Initially, all the enzyme is free, not bound to substrate. It's going to rapidly bind substrate, and so that concentration, that is the concentration of the unbound form, decreases. Correspondingly, we get more and more of the enzyme substrate complex. And then over a long period of time, even though we're following the reaction, substrate is continuing to be turned into product, but there's no net change in the enzyme substrate complex. Then we reach a point at which we're starting to convert all of the substrate to product. And so the concentration of the enzyme substrate complex decreases, and that of the free enzyme increases. So in the end, we have it all back to the original enzyme form and none in the enzyme substrate form. This period of time during which the concentration of ES doesn't change, those are called steady state conditions. The enzyme is saturated with substrate. In other words, the concentration of the substrate is so much more than that of the enzyme that as soon as the enzyme substrate complex gets converted to product and we release the free enzyme, it immediately binds more substrate. So there's essentially no free enzyme present. It's all in the ES form. So those are our steady state conditions where the concentration of ES over time is zero. There's no net change. This is our third assumption, steady state conditions. So now let's return to our expression. Here's our expression for velocity here, and remember we're moving towards replacing this term, the concentration of ES. And we know we're at equilibrium, so we can set that change of ES over time equal to 0, and that's now our equation is equal to 0, and so we can simplify it even further. So here's our simplified expression here. We have ES, the concentration of ES here. Remember, we're moving towards eliminating that from our expression, or at least putting it into terms that we can actually measure. We have another variable here, and that's the concentration of E. Let's see if we can simplify this further and replace that term. We know that the total amount of enzyme present is equal to the amount that's present in the enzyme substrate form plus that which is in the free form. So we just rearrange that expression. Now we have an expression that represents the concentration of E, and we're going to substitute this expression. This is on the lower right here. We're going to replace that into our equation here. Once we do that, we see we have a simplified expression. We want to group all of our rate constants together, so we're going to divide both sides of the equation by K1. And now we have all of our rate constants grouped together. Let's replace those with one term. That will simplify things further. So we're going to call that the Km. We're going to return to this in just a little bit. So here's our simplified expression. We're going to rearrange, do a little algebra, and now we have an expression for the concentration of ES. This is exactly what we were moving towards. And so now we can replace the concentration of ES term with something we can actually measure. So here's our expression for velocity, K2 times ES. Now we're going to replace the term we just developed, and here's our expression for velocity. But there's one more thing I can replace, and that is, remember the maximum velocity? When the enzyme is at maximum velocity, all of the enzymes are loaded with substrate. So if I know the total concentration of the enzyme, and it's working at maximal velocity, that represents the total concentration of ES. So the expression K2 times the concentration of the total amount of enzyme, that's our Vmax. And so now we have the final form of the Michaelis-Menten equation. Initial velocity equals maximum velocity times substrate concentration divided by Km plus the concentration of S. So we can plot initial velocity versus substrate concentration, and in the next lesson we want to see how we can get these values of Km and Vmax. Note that this is the equation of a hyperbola, And this is why when you plot initial velocity versus substrate concentration, you always get that hyperbolic plot. Now, you're not responsible for this derivation, and so you may be wondering why we went through this exercise. Part of that is to help you realize how important it is to think as a biochemist, as a scientist. You can't simply take an equation and use it without regard to circumstances. It's important to recognize how the equation was developed and what the different component parts tell us about how they relate to one another. So we'll see in the next lesson how we can use this equation. First, let's look a little bit more at that Km term. Remember, it's a collection of our rate constants. So remember, K1 is our rate constant for the rate at which the enzyme substrate complex forms, and the numerator simply represents the rate at which it disappears. So it's a ratio of the rate at which it disappears versus the rate at which it forms. So if an enzyme has a really high affinity for its substrate, how will that affect K1? Well, that will certainly get larger and larger. In other words, it's going to bind at a faster rate if it has a higher affinity. So as K1 gets larger, what happens to Km? Well, as K1 increases, Km decreases. So the lesson here is that a low Km is associated with a high affinity. Remember the myoglobin saturation curves? We saw a similar thing, didn't we? That is that the K or the P50 value was lower as the affinity got higher. So the significance is the same. In our next lesson, we want to see how we can relate the velocity with substrate affinity and how we can measure these experimentally, and then we can figure out what these values tell us about the enzyme.